Hi everybody and welcome. This is EPMATH234, Introductory Mathematics Applications. Our week 1 video on coordinate geometry. In particular today we're looking at the Cartesian plane. So let's get into it. A relationship between two variables can be shown in a variety of ways, including an equation, formula or a graph. What does that mean? Well, two variables, we're back to algebra. Two variables could be defined as maybe A and B. And you're not sure what A is and you're not sure what B is, but they might relate to each other in some way. Like in terms of an equation, we might know that A plus B equals 10. So if I look at a grid of values, I'm just going to make some stuff up. If A is 2, I'll know that B is 8, because I know that A plus B is 10. But they're variables. I'm not saying A must be 2, maybe A is 3. And B is 7, maybe A is 4, B is 6, and so on and so on. There's actually an infinite number of solutions I could do here, but okay, those two variables have some relationship defined by an equation. Now, a formula is going to look very different. A formula is going to look very similar. Its only difference is that we've got one letter by itself, the subject of the equation. So formulas are written as a y equals an x equals a equals sort of form. Anyway, in this one, the formula says y equals x plus 1. Well, let's look at another grid. If y equals x plus 1, let's say maybe x is 2. Well, y must be 2 plus 1. Maybe x is 3 would give y equals 3 plus 1. And again, you can see we've got a relationship going on between them. So an equation might define the relationship, a formula might, and a graph might. This graph is supposedly of a car taking off from the traffic lights, looking at its distance versus time. As time goes on, maybe it's 1 second, it hasn't moved very far. After 2 seconds, it's moved a lot further. After 3 seconds, it's moved considerably further again. So it's accelerating. It's all sounding very physicsy, but we're just saying that yes, there are relationships that can happen between two variables, and we want to find a way to be able to graph these, which is the next week. In order to do that, we need to define the Cartesian plane, which basically is what we were dealing with there. Let's look. So the graph relationship can be represented on the Cartesian plane. It also gets called the number plane or the xy plane, because normally we're going to define them with an x here and a y here. We'll get onto that. But yes, the Cartesian plane makes us plot all these little dots which define the relationship between two variables. Here's the man who invented it, or it was named after, due to his work with determining the location of a point in a plane using ordered pairs. We'll explain that in a second. But yeah, Rene Descartes. He's also the bloke who said, "I think, therefore I am," which I'm not really sure what that means, which probably means I don't exist. So anyway, when you look at a street directory, well, maybe not anymore nowadays, we just ask the phone where to go. But in vintage places you can find things like this. I'm not just picking on Dungog, I just happen to pick Dungog. Now, say we require the location E7 like it says here. Well, in here we would have gone down to the E and said, alright, I'm coming up vertically from here. We would have gone to the 7, moved horizontally from there, said E7 is this location right here. Well, it's effectively the same as a Cartesian plane. The Cartesian plane works in the same way. We've got the x-axis, okay, so instead of the letters along here, well, they're going to be numbers in a sec. We've also got a y-axis, okay, and we have a grid, same as the map did. So we number the x-axis, we also number the y-axis. So it's not a letter number combo, there's two numbers. These numbers are known as ordered pairs and form the coordinates of each point. Like there's a point, 1, 3. Same as in the last one, E7, I couldn't describe a place just by E. I needed two coordinates, a pair of coordinates. And in this case, there's a pair of numbers. And the order matters because you can see here they're referenced as XY coordinates. I always think X comes first in the alphabet, so it comes first in the pairing of coordinates. So the X tells us where to go horizontally, and the Y tells us where to go vertically, because the x is a horizontal axis and the y is a vertical axis. So if I'm trying to find the point 1, 3, well, first I'll say horizontally there's 1, vertically there's 3, and clearly the point I want is where they intersect. I don't have to write in my grid lines as long as it makes sense that that is the point 1, 3, which is different to the point 3, 1, because again the point 1, 3 was an x and then a y. the point 3, 1 would be an x of 3 and then a y of 1. An x of 3 and a y of 1 would meet at here. So whereas that would be 3, 1, this is 1, 3. Okay. So in summary, x is a horizontal coordinate, yes, and y is a vertical coordinate. And it's an ordered pair because the order does matter, x, y. So the origin is a special point. It's right in the middle. It's naught along the x-axis. It's naught along the y-axis. In other words, we've moved, it's like everything starts in the center at the origin. I've moved naught horizontally, I've moved naught vertically. I'm still at what we call the origin. There's the point we just did, 1, 3. Here's another point, -1, -2. Oh yeah, -1 was the horizontal movement. That was the x, so we went to here. And then the vertical movement was -2. So whether you think of it as in it's -1 on the horizontal, -2 on the vertical, which clearly meet here, or it's like saying I moved 1 backwards horizontally, I moved 2 downwards vertically, and I ended up here. It gives the same result whether you think of yourself walking there from the origin, or whether you do the map thing where you go down from the -1 and across from the -2. There's another point. They don't all have to land slap bang on a whole number. Here's 1.5. Yeah, 1.5's coming down here. -2.5 is halfway between -2 and -3. So yeah, they don't have to be exactly on. They could be surds. We don't need to go there. So these little blue background slides, you can pause if you want. There's little multiple choice things just to check. So pause now. All right, opportunity missed. X, Y, well, the X direction I've gone to -3 and the Y direction I've gone to 2. So it'll be a -3, 2. Yep, that was B. What about this one? In the X direction, horizontally first, I've gone -1. Vertically, I've gone -4. So there it is at A. Yep. Another one, pause again if you want to have a go. It's easy to get wrong, but just think, how far have I moved horizontally? I haven't moved anywhere horizontally. How far have I moved vertically? Not down 3, I've moved up 3. Absolutely. I've moved nowhere horizontally, I've gone up 3, so it must be the point 0,3. Great. So that was just the intro to the Cartesian plane, which we want to use throughout coordinate geometry. Now, the next thing we need to introduce is the gradient. Now, if we join any 2 points on the number plane, we have a straight line. Number plane, we're going to be calling it y and x. Here's a point, and if I join them, or whether I join them or put a line straight through them, I form a straight line. Now, we are going to talk about that straight line, forming an equation for that straight line next week, but we need to first introduce the gradient. So before we can define the relationships between the x and y coordinates on a straight line, one of the things we want to know about is its gradient. In other words, its slope. It's the same thing. So the gradient of a line is the measure of the steepness and direction of a straight line. So we're going to be talking about it as in steepness, as in, well, I know, like a train. I've heard of trains being described as they can go up a maximum of 1 in 60 slope. So that's not very steep. A 1 in 60 slope would be something like, if you need to get 1 metre high, you need to travel 60 metres along. So that's not a very steep slope. What if the slope was 1 metre, 1 metre? Well, that's a very steep slope. So we've got a steepness. The 1 in 60 would have been written actually as a 60th. The 1 in 1 will be written as a 1 on 1, which is 1. But that's what we're getting to, okay? I'm jumping the gun. And it also says the direction of a straight line. Both of the straight lines I drew here were heading uphill. I walk along from left to right, so both of these ones I drew as positive. But there's negative gradients. There's a negative gradient taking me down. So we've got the steepness indicated by a number, and the direction of a line is indicated by a plus or minus. So gradient can be positive or negative. There are other options, but firstly let's look at my PowerPoint ability here. Be prepared and amazed. Positive gradient, again, walk along from left to right, cycle if you will. Look at that. Okay, so left to right, I've gone uphill, that's positive. But if I go left to right and I go downhill, that's considered a negative gradient. So gradients are either positive or negative, or two other options. Maybe there's a zero gradient. I don't go up, I don't go down. Yeah, that's a zero gradient, zero slope. If the ground has a zero slope, it's perfectly flat. The other option is it could be completely vertical, which we use the term undefined. Now you might think, well, isn't that infinity? Isn't that infinitely slopey, a slope of infinity? Well, yes, you could say that. You could also say it's negative infinity if you want. The bloke could be travelling down. But either way, the number infinity isn't a number, even though I just said the number infinity. Infinity is not a number, it's a concept of going on forever and ever. And infinity is undefined. You know, what does it equal? Well, it's undefined. So we just stick with that term. You're not wrong to say infinity, but we call it a positive gradient, a vertical gradient, undefined. Now the gradient itself is defined as vertical rise over horizontal run. Like that train track I was talking about before was, if I wanted to get up 1 metre, I needed to go along for 60 metres. That's why I called it a 1 in 60 in old-fashioned sense, is a 1/60th gradient. So it's always a vertical rise over a horizontal run. So the directions matter too here. The run is left to right. We said that it's like the direction we read. We go left to right. And the rise is clearly going up. Now sometimes we'll go against that and we'll bring in negative signs. Okay? But the gradient is always the vertical rise over the horizontal run. You can also call that the change in x. The change in y over the change in x. By the change in y, it just means the change in its vertical location. So here, from this point to this point, the change vertically was this distance. And the change in x from this point to this point was that. I've gone that horizontally, I've gone that vertically. So it's the change in y is the vertical rise, the change in x is the horizontal run. And it says here we'll use the letter m to denote the gradient. That's a fairly standard thing amongst most textbooks, mathematicians. So m is the vertical rise over horizontal run. Now to look at a few common gradients that we'll see. There's one. Now it goes through 1, 1. It goes through 2, 2 and 3, 3 and 4, 4. But what's its gradient? Well, for every 1 it goes across, it goes up 1. So its gradient is 1 vertical rise over 1 horizontal. 1 on 1 is 1. It doesn't matter which points I pick. I could pick these points and draw a triangle here. Its vertical rise is 2 over horizontal run of 2. 2 on 2 is 1. Clearly you can see we've got a gradient of 1, whether I do it in the little boxes, the rise of 1, horizontal of 1, or if I choose it over this length. The rise is 3, the run is 3, and 3 over 3 is 1. So the gradient of that is 1. The gradient steeper you would expect to be a larger number than 1. And if you look at any points like this point and this point, just draw a triangle here, which is a right angle triangle, and we've got a horizontal run of 1 and a vertical rise of 2. So again, it's vertical and horizontal, 2 on 1, it's a gradient of 2. We don't have to write 2 on 1, 2 on 1 is 2. Any number on 1 is just itself. And there's a gradient of a half. That hopefully makes sense. It's not as steep. So here's a point here and here. It's gone 1 rise over 2 runs. Or again, I could have picked these points and said 2 rise over 4 runs. Well, 2 over 4 does simplify down. There's 1, 2 in there. There's 2 2's in there. It's still a half. So there's some common ones. And the only difference with these ones which are going downhill is they're going to be negative. If I wanted to find, again, I'll pick any old points. The vertical rise in moving from here to this point, well, it's a negative 2. I didn't go up 2, I went down 2. Horizontal run is still a positive 2. I've just gone from left to right. We always just go left to right. So the gradient there is a minus 2 rise, because it's actually a drop over a 2 run. Minus 2 on 2, well 2 on 2 is 1, is a minus 1. So you can see we've got this symmetry here. There's minus 1. A gradient of minus a half is symmetrical to the gradient of a half, and the gradient of 2 is symmetrical to the minus 2. So there's some common gradients we'll see. Here's some examples. Now they're already gone through in your course notes, but let's draw a triangle here. And we'll say, well, from this point to this point, I'm going to draw my triangle like this. I really need to get better at drawing, don't I? My vertical rise is clearly a 1. My horizontal run is a 3. I've gone 1 box over 3 boxes. So my gradient is 1 over 3, which is a third. On the next example, well, you can see we've gone from this point down to this point. And again, it's a right angle triangle. My vertical rise, well, it's not a rise. Left to right, I'll put in my horizontal run first, is 2. Again, I'm saying I'm going from this point to this point, left to right. But it's not a rise, it's a drop. 1, 2, 3, 4, 5. It's a minus 5. And what's minus 5 divided by 2? Well, minus divided by positive is a minus. And 5 on 2 is still 5 on 2. Yeah, you can call it minus 2.5 if you want. You call it minus 2.5 if you want. They're all the same answer. So, the gradient of the following line is, pause if you wish, but I'll draw a triangle wherever. Now, I'm not going to draw a triangle here because I can't even read that point. I don't know, is it a third, is it a quarter? Pick points where you can clearly see it going through, like the crosshairs on a target. You can see the line going through here. That's a good triangle to draw. Its vertical rise, it's gone up 3, it's gone across 1. It's clearly a 3 on 1. It's answer A. Let's do another one. Pause here. Okay. I like to say automatically, it's definitely a negative gradient. I want to get rid of those two. Even though I might be trapped and look, say vertical, 2 on 2 is 1. No, the answer isn't just put this number on this number. I've got to draw a triangle. Sure, it's cutting through here and cutting through here. But if I walk from left to right, my horizontal run might be 2, but my vertical rise isn't 2. It's coming down, it's minus 2. So you're right to think, look, the two sides of the triangle, it's going to be a 2 on a 2. That's okay, but don't forget there's a plus or minus involved here. And clearly, here's me, well, this will be good, walking along it. Excellent. And I'm going downhill. It's a minus gradient. It's 2 on 2. It's a negative 1 gradient. No more drawing. The gradient of the following line is, again, you're positive. You're gone, you're gone. It's definitely a positive gradient. It's cutting through at convenient points here. Vertically, I've got a 3 side, and horizontally, I've got a 2 side. Yeah, it's a 3 on 2. Great. Another one. Overboard. Again, I might guess that's 1.5, but no. Choose some nice points where it's cutting. There we go. It's cutting through there and there. You can see it's a negative gradient by positives. And vertically it's a 1, horizontally it's a 2. So vertically it's gone down 1 over a run of 2. Yes, it's a negative half. It's D all the way. Great. Now the last bit we need to look at is you don't always have to draw it. You don't always have to get given a graph. You can use a formula. And here's, you don't have to know the derivation of the formula. Here's just so it makes sense. So it's not something that's necessarily memorized. It's logical. We said before the gradient was a change in y over the change in x. Now look, here's the point I've defined as x1, y1, and here's one called x2, y2. Well, x1, y1 must have an x coordinate of x1 and a y coordinate of y1. x2, y2 has an x coordinate of x2 and a y coordinate of y2. And here's my triangle. Okay, so what's the length of each side of the triangle? Well, I can see I'm going to get the horizontal distance by x2 minus x1. This number minus this number will definitely give me the gap. Same on the y, this number minus the y1. So they're my sides. So all I've got to do is say, look, the change in y is this over the change in x, which is this. It's that thing over that thing. So there's that formula. The gradient can also be called y2 minus y1 over x2 minus x1. So that's our gradient formula. Hopefully not necessarily a memorized thing, because if it makes sense, it's not so much a memorize. It's changing y. Yes, so the y is on top. Changing x, yes, the x is on the bottom. And it's the second value minus the first. The truth is it wouldn't really matter if we did first minus second on top and bottom, as long as we did the same. Like in one case you'd get the opposite answers on top and bottom, which would cancel each other out. Again, overboard, David. Focus. So let's look at this definition of points as an x1, y1, and definition of points x2, y2, and this formula. So if we get given this question, I don't particularly want to draw it. I could, but let's not. I know that now it doesn't matter if I call this point 1 or this point 2 or the other way around. It makes no difference to me. So I'm just going to go in order. Now, the main trap I see people is trying to call this maybe x1, x2. No. We know that's an x and that's a y. Every set of ordered pairs, every set of coordinates is an x and a y. But I'm just going to call you can be the 1s and you can be the 2s. And now I'm going to use my formula. The formula said that gradient equals y2 minus y1 over x2 minus x1. So the y2 is clearly a 2 minus the y1 is a minus 1. Don't get trapped here. You don't have to bracket, I do it for clarity. The formula had a minus, the number's minus, yes there are two minuses there. The x2 is a minus 8, the x1 is a 4. Alright, look what I've got, a 2 minus minus 1, minus minus makes plus, so that's 2 plus 1 is 3. On the bottom, minus 8 minus 4, don't fall in the trap of thinking that, oh, does that make a plus? That's like a number line. If I was standing at 0 and I went back to minus 8, and then someone said, now take 4 of it, I'd go back another 4 places. Where would I end up? I'd have to end up at minus 12. 8 steps back and 4 steps back is 12 steps back. So I've got a 3 on a minus 12. I know a plus divided by minus is a minus, and I know 3 on 12 can simplify down to minus a quarter. Technically I'm not wrong to leave it as minus 3 on 12, or even 3 on minus 12, but we should go to the simplest form answer, which is minus a quarter. There's our gradient. So for the previous examples we did, where we had them graphed, we could have just used these points and said, well, the gradient is, once again, let's call it xy, xy, you can be 0.1, you can be 0.2, so y2, I'll write the formula again, of x2 minus x1. The y2 is a 3, minus y1 is a 2, over x2 is a 4, minus x1 is a 1, 3 minus 2 is 1, 4 minus 1 is 3. Yeah, there's a third. We can see it there anyway. The vertical was 1, the horizontal was 3. But the formula does it for us. And the formula will always give us the plus or minus answer. It'll give us the correct answer. Like here, watch, the formula will give us a negative gradient. We already know what was the answer. 1, 2, 3, 4, negative 5 over 2. That was the answer. Let's look at the formula. Give it to us. And again, no, it doesn't matter which I call 1 and 2, as long as it's xy, xy. You can be 1s and you can be 2s. So y2 is a minus 1, minus y1 is 4, x2 is a 1, minus x1 is a minus 1. I've got that minus minus happening again. Minus 1 minus 4 is a total of 5 steps backwards, so minus 5. 1 minus minus 1, those two minuses make a plus, so it's 1 plus 1. And it doesn't matter whether the minus is on the top, or if there's a single minus on the bottom, or whether it sits out the front. Because a minus divided by a plus is an overall minus. There's the same answer we got before, so yes, we could have done it that way. So just a quick pause if you like. The straight line passing through there and there. Okay, xy, xy, you can be 1s, you can be 2. My gradient is a y2 minus y1 over x2 minus x1 equals 1 minus 4 gets me to a backwards minus 3. 0 minus minus 2 is a 0 plus 2. It's a minus 3 on 2. It's D. We got it right. Thank you. That was that week. Week 1. Bye.